Okay, guys, so today my presentation about a simple question: what you can get out of near-surface geophysics in terms of subsurface properties and processes. To answer this question, I will go through some of the basics or most famous resistivity geophysics technique, such as resistivity, ground-penetrating radar, SIB, and fiber optics, temperature sensing, and I also go through some case studies outlining hydrogeophysics and biogeophysics. Okay. Okay, so the first technique I will describe really quick is resistivity. Is this fine? Can you hear me? Or okay. Okay, for resistivity technique, actually, I will talk dipole, what's called dipole configuration. Dipole because you have the current electrodes and the potential electrode are separate. Okay, so the distance between the current electrode and potential electrode determine two things: the horizontal resolution. In other words, how can you distinguish between closely spaced targets? If you have different target closely spaced, how you can distinguish between them? Most likely, in most inversion out there, the lateral resolution is just half the electrode spacing. So if your electrode spacing is 1 meter, your lateral resolution will be 1 meter as well. Vertical resolution is a little bit different. It's based on how these 4 electrodes are arranged. There are several arrangement you can make. For example, you can make the current electrodes at 1 and 6 and switch potential electrode at 5 and 2. This will called, Schlumberger, for example. And yeah, so it's the method is fairly simple. It's based on the Ohm's law. So actually, you inject the current, you measure the potential difference, you got the resistance, you convert it to resistivity based on the locations of these 4 electrodes that you have. Okay, when this method doesn't work, some cases this method doesn't work. For example, if you have a very high resistive surface, this method will not be able, sometimes, okay, say you have a granite. Sometimes you cannot inject enough current into the ground so that you can get meaningful measurement. In fact, there is an alternative geophysical methods. I will just try to hurry up. Frequency domain called frequency domain electromagnetic. That can work in any terrain. So usually people start now to substitute resistivity with frequency domain electromagnetic, especially in very high resistive environments. Okay, so another method I will describe really quick is ground penetrating radar. As you can see here in the picture, this is one sort of the instrument. You have transmitting antenna, receiving antenna. This antenna could be separate, like what you see here. Separate transmitting antenna, separate receiving antenna. This is called non-shielded. It has a benefit over what is called shielded. Shielded means it is these both enclosed into a box, big box. Okay, so the benefit of this one, you can do same-B measurements. In other words, you can take measurements at fixed point in the Earth's surface and increase the spacing. That gives you velocity estimate of the subsurface. You cannot do that with shielded antennas that is in the box, but it has a drawback. The drawback of it is sensitive to all, around noise around the instrument, like trees, anything around walls, infrastructures. Okay, so GBR methods. Okay, the basic idea is for this to work, it's based upon a big assumption called low loss assumption, which means for this to work, you have to have in the subsurface low conductivity, low permeability, magnetic permeability. If you have high conductivity, these electromagnetic waves from the transmitting antenna will fully attenuated. very shortly. This is one of the drawbacks of this method. So the basic idea is just you send the electromagnetic wave. This electromagnetic wave reflected back at any boundaries where you have different materials that has either different electric conductivity, different dielectric permittivity, or different density, as we see in a second. Again, there's two modes of measurements you can do with this. One, you can estimate the velocity of different subsurface layer by doing what is called CMB, by separating this at fixed transmitter and receiver at fixed distance apart, or can fix the spacing between the transmitter and the receiver and measure common offset profiles. We will see both types in a second also. Okay, now I will start some case studies. Okay, so the first case study I chose is imaging trees, roots, and the trees trunks. So the reason for imaging tree trunks to determine the health states of trees, of different tree species. This is a cross-section of oak tree trunk. What we are interested here is the middle part here. Okay, so for a tree to be healthy, this middle part has to have high resistivity, if in case you run resistivity as this case. And the outline as you go in the outward, it has to have low conductivity, especially at C here. Okay, so for tree trunks, people use two methods: resistivity method and seismic methods. Here I chose to present resistivity. It's simply, you pick any tree, put electrodes around the trunk, and it's the same principle like surface-based resistivity. You inject the current, you measure the potential difference. The trick part about this is how to invert the data, because most commercial software, I'm not sure about SolarSting or AGI, you cannot create a mesh like that. So this is the tricky part, but good news, there is available open source code that can do this for you. So this is not a problem. So here, this is just electric measurement setup. You have here assumed decay, any sort of disease or bacteria that tree has. And here you just, again, you plant the electrodes around. The number of electrodes depends on the diameter of the tree you have. So, and you measure the measurement and invert the data. And hopefully, if you get high resistivity at the center, that tells you this tree is good. If you get low resistivity, this is basically the general, that tree is bad. How about trees root? Trees root has different setup. So for this study, I chose what they did. Here's the trees. These star lines representing 2D resistivity line everywhere around the trees. E, B, C, D is just GBR tomography measurements. These people just, make trenches around the tree in all directions around the tree with half-meter depths and measure the radar tomography. Why they measure the radar tomography? Two things: to image the tree roots and measure the moisture heterogeneity around the tree. Okay, so here's the results. This is tree trunk. So as you can see here, you have low conductivity almost in the middle. They call this weakly, they call this severely, infected trees. They didn't show any healthy trees in their study. Here's the results of resistivity. One thing, I have a quick comment about this. They just, as you can see here, they have several two lines. They combine them to make a 3D image, which is, well, some people doesn't like it because, yeah, you can simply just invert 2D sections because you are interpolating a lot around the tree. So here they predict this anomaly here as the tree roots. This anomaly at various variable depths, such as here, half meter, and to 1.9. And what they did with radar tomography is they convert the travel time between the transmitter to receiver to velocity image. And from this velocity image, you can straightforward, using equation called TAB equation, measure the volumetric water content around the tree. So as you can see here, the volumetric water content is fairly high here at the tree root location, which is fairly consistent with resistivity.
Why were you so concerned about this tree?
Well, we have a group meeting. They were talking about this, so I picked this study for them. They are interested in imaging tree roots. So, and one more thing about the tree trunks, because I was visiting the site recently, the site here, I don't remember the name. I was told that, oh, okay, I noticed there is dead trees, there is live trees in the same location. So I was wondering, okay, how about if you do something like that? So this is for myself, but this is for the people who was discussing. So. Okay, so another case study. I'm sorry, we have this as a group discussion recently. So it's groundwater, surface water interaction using time-lapse resistivity measurements. This data, I was involved in this study. This data was in Hanford. This is here, Columbia River. And there's a groundwater aquifer here. So they're trying to figure out where along the Columbia River there is enhanced exchange between the groundwater and the river. In order to do that, they make a 3D resistivity array here and measure time-lapse, resistivity measurements. Okay, the reason they select this location here, specifically here, because other data, like IB data, tells them that there is a value channel here. So two reasons for this study was to verify there is a value channel. Second, to find a quick way, another way, alternative way to invert the resistivity data or to interpret the resistivity data fast way. Because traditional ways was based on just comparing different time-lapse images. Where this method with this, the model, if I remember, was more than 100,000, mesh cell. But you can process the whole data within half an hour. While you take in the old method, it's inaccurate and not accurate, and it takes forever. So anyway, so it shows this location because there is a value channel somewhere here, and it does 3D resistivity. I'm sorry, I'm quick. So, okay, so they measure two things: the stage, the Columbia River stage variation, and of course the resistivity at different time lapses. Okay, so in order to process the data, we used a time frequency analysis tool called the S-transform. So we do the time frequency analysis of the stage data, and you notice at the dominant periods on this stage data, and you notice the dominant period at each element of the 3D model. So here, this element was assumed to be inside the value channel. This element was assumed to be outside the value channel region. So if you notice here, you have a period of 4 that's in the stage, but not here. That tells you the stage variation derive the resistivity variation at this point, at this element in the underneath the 3D array, which gives you there is a connection at this area between the river stage variation and resistivity variation. So by this, just this plot, we confirm that, okay, at this location, there's a value channel because you see the same period, but you don't see it here. So to investigate this more, we process the whole data that we have at this 4 period, And you notice the 3 the pictures. So we done the analysis of this was 4 and 8. So we did the analysis at 8. And as you can see here, this box here, this is where the value channel is supposed to be. So you have here high anomaly at the value channel location, but in the same time, you don't get the location of the value channel, you get the variation of the strengths of the exchange. For example, here the exchange is very high, here exchange is very low. So in other words, we get temporal variation between the stage and the stage and the aquifer, and you know exactly when there is high exchange, enhanced exchange, and when there is no exchange. So this was the study. Okay, another study, case study, back to GBR, is about how to estimate snow water equivalent and snow density from GBR measurements. Here an image of a GBR system. Somebody is collecting data. Here's the two types of data collection I described. This is a common offset measurement where you have fixed distance between the transmitter and the receiver, and you just move along the profile. And here, the common midpoint, where you have a fixed point in the Earth's surface, and you move the transmitter and the receiver equal distance away from this point. So the CMB here, this interface is supposed to be the snow ground interface. Why you see it very clear like that? Because again, this GBR method depends on the direct, mainly the direct permittivity contrast between two materials. So here, obviously, you see it very clear because there is enough or high direct permittivity contrast between the snow and whatever underneath it. Okay, so those guys here, in order to measure this snow equivalent, water equivalent, they did common offset measurement to get the velocity, and they convert this to depths to know the depths. And in addition to that, here's the CMB location of this one. In addition, they came here and make a manual measurements about the density and snow water equivalent using, I think, a snow fork at this location to compare between the results of GBR and the results of these manual measurements. In order to get to the final measurements using GBR, you have to, solve a set of fairly easy equations. Until you get there, I will not go through that. But here's the final results. Here's the predicted velocity. Here's the snow depth using the manual. And the GBR, if you can see, it's pretty close. Snow density is pretty close. Everything is pretty close. One thing I forgot to mention here is this snow is easy. It's dry snow. It doesn't have any liquid water in it. So in other words, this velocity here is just a function of density of the snow. So this looks like straightforward for this case study. But it will be far complicated if you have water inside the snow. Why? Because the velocity will no longer depend on the density alone. It will depend on the amount of water inside the snow. Okay, one thing I have to mention here is the unit here is just wrong. And another thing, if you can see here, the manual measurement predicted the snow water equivalent and the snow density here. But GBR continuously can estimate the snow water equivalent snow density at any place along this interface here. Just multiply these two quantity and you got your snow.
Can I ask a practical question? How fast can you drag a GPR sled?
Okay, for this study, they make measurement every 5 centimeters. But you can attach it to ATV. Some people attach it to ATV and they run slowly. But in case you are too fast, the system is smart enough and make a beep to warn you that this is too fast. But most people, drag it like that, since they need high resolution measurements. Okay, so that's interesting. Okay, so case B, if you have a complicated scenario, if you have a water there, so you need to measure another quantity attenuation of the radar, this radar signal. Again, those guys gives a set of relationship that you can easily follow and you go through this. So again, those people use the snow fork at some location along the profile, calculate the velocity model from reflection tomography, very straightforward. And here is an example of CMB. Here you can see, and they made a smart thing. What they did is that, if you notice in the picture here, they uplifted the instrument. Why they uplifted the instrument? Why they didn't do that in this dry snow? Because dry snow, they assume homogeneous snow. But if they do the same approach here, same B, it will be different because you have lateral heterogeneity. That's why they raise up this to get the reflection from the snow-air interface. And this will help them during the estimation, one of the equations to estimate the snow properties.
So you're calibrating the air-snow interface?
Yes. So, okay, again, pretty fast. So this is pretty complicated because you have water. So they estimate a velocity model. This is the CMB, this is the top snow, this is the bottom snow. And this is the results from the snow fork. This is the water content. And they go through their equations and estimate the water content. Here, the square here is where the snow fork, and this is the actual measurements. So it's pretty close. Same thing here. This is the snow dynasty. This is the estimated snow water equivalent. So it gives pretty close or fairly consistent results. Again, I would stress on the value of this GBR, because as you can see, you get lateral continuous measurements of these properties of each of these, while using the snow fork you get at one location. So
what are those error bars?
this is based on this estimation.
What's the confidence interval?
Yeah, this is a confidence interval.
95?
I don't remember. It looks like
64?
Yeah. Oh, this is blank. I was supposed to put something here. Okay, so another case study. This is Biophysics. So this is monitoring coupled microbial and geochemical processes using SIB. Okay. This is very interesting. SIB is a fairly recent technique. People still using this technique in the laboratory. A very few studies use this in the field, but this is one of these studies that use this technique in the field. But I would say this is controlled fields. You know everything about this field. So this field in Colorado. And their big question is, can we predict the groundwater geochemistry and the mineral precipitation using this type of measurements? This type of measurement is spectral-induced polarization, the difference between it and, for example, resistivity. So resistivity is sensitive to the bulk volume, but this is only sensitive to just the interface between the fluid, if you have fluid, and the grain. So using this measurement, you are focused on the pore space. In other words, if you can differentiate pore space that has mineral in it, that has fluid in it. This is very useful. But again, it's a fairly new method. There is no inversion. There is some inversion for it, for this type of data, but it's not, well enough. So again, those guys use measurements, SIB measurement here. So, okay, so what they did, you have a bunch of borehole here. They inject some sodium acetate and bromide here and here. They inject here over 68 days and here over, I think, 21 days. And they measure SIB along these two lines. This is groundwater flow direction. So one profile is perpendicular to it, another one is parallel to it. And yeah, so SIB measurement, I can go to the basic of it, but let's pass that and go to results directly. Okay, so for SIB measurement, you measure two things. You measure the phase shift between the applied potential field and the measured potential field. And you measure the magnitude of that field as well. So the phase shift and the magnitude. From the magnitude, you can get invert for resistivity and the phase shift. Yes, you can get phase shift inverted model based on the phase shift. So they assume that the bigger the phase shift is, that tells them there is this area where it has bigger phase shift. This belongs to area where there is mineral precipitation, reduction of minerals. This is what the whole conclusion. And support their idea, they got the talk sample from this location here and indicates it contains sulfide and iron and sulfate. And one thing here, as you can see, this resistivity measurement is not very sensitive to the bore scale, the fluid bore interface. It's fairly, it increased a little bit, but here it's totally different. The phase is the measurement that tells you exactly what's going on in that interface. What resistivity is just as expected. It doesn't give you much valuable information. And here, this is an image of the sediments they took out from these locations. This is before they inject the acetate, and this is after. As you can see here, there is the sulfide mix this color to this. So it's a fairly fairly good results, but they didn't explain actually. They inject acetate here, but why the anomaly is here? Why the anomaly is shifted? They didn't explain why is that. They just said, okay, last year we got the same results. So again, this is a new field, I guess, and they still have people actually focus on lab measurements to try to understand the anomalies they got. So
as the sulfate is being reduced actively as the data is being taken, that's creating the polarization anomaly?
Yes. But they take the measurement after sometimes. So
if there's no reduction going on, you won't see that phase.
this is immobilized sulfide. It's precipitated. So you will see it.
Okay.
You will see it. Here, before the injection, you don't see it before you inject it. But after, even, you will see it.
Okay.
Okay, so this is, go back to GBR. This is very simple. Here, this is my paper, published in 2010, not 9, obviously. So here, I based this on theoretical forward modeling of fractures, horizontal fractures. So here, in the model 1, simulate widely spaced fracture, horizontal fracture, and the closely spaced fracture. In all three models, actually, but I change the fracture content. So here, this widely spaced consists of air. This is air. This is water. This is water. This is air. This is water. There's another one I didn't show that has air, water, air here. So what I'm trying to figure out is how you can differentiate between them using GBR. So for example, for air-air fractures, you have a widely spaced set and a closely spaced set. All fractures are filled with air. Here, I run the S transform time frequency analysis of this signal. I get no shifts in the frequency content. Here for the water, same thing. I only get a little bit of anomaly here because as the wave goes from widely to closely spaced, as it enters, it causes this shift. Here, air-water, I have clear shift of the frequency content. To verify this, we did another modeling. What we did is that we get this model, fixes this set, and try to fixes this set and trying to increase the dielectric permittivity of this set. So, in other words, we try to simulate water using different dielectric permittivity values. So, here, this is the original case where dielectric permittivity, there is no change in dielectric permittivity. Here, you have a change of 10. For the closed space, 20, 40, 60, 80. As you increase the water content, you have enhanced shift. So that tells us there is a dependence between the dielectric permittivity change and the frequency shift. Here, in our simulation here, we try to simulate fractures that below the resolution limit of the GBR, or in other words, below the 1/4 of wavelengths of the transmitted GBR signal. So in all these, yes. So for example, this is 1 centimeter. So it's the easier you can predict if it is fairly wide, but we'll try to make it harder. Okay.
How sensitive is the results to the aperture of the cracks?
I didn't study that. I didn't study it.
Okay.
But actually, there is data that I got from here. Snow range. I was supposed to create a new whole set of forward model to study this effect, the change of the thickness of the fracture.
Right.
But I didn't have time for it. So, but I plan to do it sometime. Okay, so another case study. This is, I think some people here know about it. It's fiber optics, DTS data. It's just a cable, fiber optic cable. And you measure the temperature at every 1 meter along this cable. So this, well, fairly new again. And people use it a lot in hydrological application to study, for example, groundwater, surface water. So again, I was involved in that study. It's the same study as the resistivity at Hanford site. Here's the Columbia River. All what you do is just lay down the cable. It could be a kilometer length, 1.5 kilometers, 2 kilometers. And you get high temporal and spatial temperature measurements. Okay, for this case, it was 70 days. Just imagine 70 days of measurement every 5 minutes. So this is huge data. So again here, okay, what's that? Okay, here's the value channel again, value channel area. And here's outside the value channel. This is the same. Okay, you can consider it as testing, as confirming that there is a value channel here. So this is a time series. The value channel, this outside the value channel. We did the same thing as before. We just take the time frequency analysis of the river stage and time frequency analysis of a point inside the value channel and time frequency analysis of a point outside the value channel and to compare between the periods. So here, for example, you see at 4 and 8 again, dominant period here, that you see it here in the stage very strongly, but you don't see it in non-exchange area. To investigate this more, we run this time at 4-day period. We run the time frequency analysis on all the data that we have, and we get 2 high anomalies actually at the value channel location in addition to another location here. And this is for 1 day period. It was everywhere. It was in the exchange and non-exchange. You got nothing. It's fairly homogeneous. So this is suggests that this is a good tool to process the data and tell you where is the enhanced or the value channel is, or any changes between the groundwater and surface water. Oh, thanks. I'm done. That's good. Okay.
I do have a question earlier on when you were talking about resistivity and GPR. And you said that it's good if you've got highly resistant materials and so on. But getting into like clays and things like that is particularly problematic. Like, what are the environmental settings for the?
Well, in case you in case you have clay, you can measure with clay. There's some tools that you can measure along with the resistivity is induced polarization. So induced polarization, if you do the same, and you can do the same measurements at the same time, resistivity and induced polarization. By comparing the inversion of the two, you can, verify if there is a clay or not. This is one. Yeah.
But like up in the Laramie range, we have these really coarse granitic soils that are like essentially bruised, and they just, for a while, they're chunks of sand and stuff. There's not a whole lot of soil structure. I mean, is that still fine to do?
Well, if it is very high resistive as you describe it, if it is very dry, is it dry?
Very dry.
Yeah, is it dry? And you have, and if you're looking for, it's problematic, but you can, usually we get rid of that by using some sort special type of electrodes called non-polarized electrode to increase the contact resistance between the electrode and the ground. This is one. Another, if we don't have those types of electrodes, we can just dig a hole and add water and salt, and we can do it. And another option, if you looking for the first 30 meters, say, you can use, relax your mind, forget about resistivity, you can use frequency domain electromagnetic, like GEM2, that we will have, I believe. And again, people start using that a lot.
Yeah, and in fact, we got one other option too. We're getting a high-powered transmitter, so you could also dig a hole. Potentially, if you can't dig a hole, you just increase the surface area of the electrode and put more power to it. What he's saying really is for the standard low-power systems that are all built together with transmitter receiver. They usually do 200, 250 watt maximum. So, and they do that as a constant power sort of thing. So in high resistive environments, the current goes down, the voltage goes up, but then you sort of run into a limit that those systems only can go to a certain voltage.
Mm-hmm.
All right. Well, we're gonna our systems basically are similar, except we've got the addition of an external high-power transmitter that works up to 10 kilowatt. So generally, those get used in the mining industry or deep applications. But if you're in a high-resistive environment, it could also be used for that. We're actually pumping high voltage even at lower currents, so that you get more reliable signals. So we've got some options.
Do you think you will got over voltage?
Well, that's a slight risk. It depends on your scale. So I mean, we've got options a little bit to overcome the high resistance problem. But I mean, it's not overly practical for some depths, especially really shallow depths, if you're going to try to do high voltage because of what he just mentioned, sort of an overdriving problem. So we've got some options there. Probably though we'd want to attack something like that with an EM instrument or something like that first, because depending on our scale and how resistive it really is, we might get more information out of it to start. But yeah, actually we're accumulating quite a number of the tools. The one that we're not really focused on, at least in the short term, is that spectral IP. So we're going to stick, at least in the short run, to a time domain instead of a spectral response. And part of the reason for that is, as Mehrez said, it's fairly new. It's a fairly new avenue of a study. And it's not so hard from the data collection standpoint. There are tools out there to do it. It's a bigger problem from the theoretical inversion standpoint of what we actually do with the data. So, I mean, we've got possibilities for research projects or potentially for the faculty hire that Geology is talking about in hydrogeophysics. If that person is sort of focused on spectral IP analysis type of things, that might be really useful. If not, I mean, I'm sure we'll jump into it at some point, but it's a little harder to quantify directly what frequency ranges of the IP might actually be representing different materials. In fact, there's been lots of people that have focused on spectral IP more for like NAPLs and contaminants, and trying to use spectral IP like you would use a gas chromatograph to basically tell you what contaminant is in what area. But from our end, it's also sort of there's an IP response just in water and pore space, and constricting the pore space can give an IP effect. So that's more of the focus for, sort of a hydrogeologic standpoint. So we're going to have a little less ability to do that kind of stuff. As far as I'm aware, we're planning on getting the GPRs, to probably do and work on some things like this. We have some access to somebody else's GPR, I guess, that has a couple antennas right now, but the facility is planning to get some more radar, because I think in a lot of ways the two things like we were discussing here that we have to overcome are the high resistive environments. We're going to have a lot of them in the mountains where there's not a lot of soil, or the soil that's there is really dry and undeveloped. So we've got to address that problem. So it's going to be probably electromagnetic and GPR at first, and then if certain environments might allow us to do some high power res, maybe.
Maybe that, I mean, it gets down there in soil, there's not a lot to do about it. I'm wondering, like, right after snow melt, when everything is pretty well saturated, would that be a useful time to go out and do some of these tests?
It'd be a useful time for the res. It would be a little less useful time for the res and the EM kind of thing. It's like res and EM, GPR and EM would be good things to do while it's actually still frozen, where it's more resistive. Res, on the other hand, is kind of the inverse. You get a little better connection and a little bit more current transfer, typically, especially on low power systems, when it's already sort of saturated and the ground is not frozen.
Could you go back to your your forward calculation of the electromagnetic crack response?
This one?
Yeah.
Yeah.
So, what's the center frequency here?
2010, I think 200.
100 megahertz?
200 megahertz.
200 megahertz?
Yeah. Oh, I don't have, this is my laptop.
So my question is, obviously, you can't pick out discrete things. The signal's all interfering. It would need to be detuned to actually pick out. So the overall response, for instance, in the top one there, which I believe was dry, where
yes,
it modulated the crack frequency, is that that's all tuned up. And so if we saw that, would you waveform model it to try to get the crack density as a function of depth? Or what would you do if you recorded that in the field?
Well, first of all, we record thousands of that in the field. But the way we do it in the field is that I'm looking for stuff like that. So when I do study GBR, studying fractures, I'm looking for water, for example. So I'm looking for water, I'm looking for that shift. Once I get that shift, I can run the whole thing in all the radargram I have with thousands of these, and only reconstruct the water location and ignore everything else. So what let's
say I'm interested in the dry crack density.
Okay, so, well, you can pick the frequency here. What's the frequency shift here you got, or what's the frequency value here? And you can run the same analysis on all radar grams that you have at this frequency to reconstruct the dry and ignore everything else.
I think you'd have to have a pretty good attenuation though of the wavelet.
Mhm.
It's like
Yeah.
these approaches work well when there's a significant contrast, but when the phase shift or the frequency loss is really small, I think that would fall within the error limits. That's the only thing I'm wondering about. I mean, and that partially is going to be due to crack size and signal
Crack fill.
frequency and crack fill and all this sort of stuff. So it seems to work well when there's a big, like when the cracks are filled with water and there's a huge attenuation of the signal. But I don't know. I haven't seen anybody really look at, you know, as you get sort of back to just that first case where it's air on air and just crack density, making that same argument with a much more narrow frequency loss.
Was that fiber optic that was brilliant scattering?
Which one? The
In Hanford there, where you're getting the temperature field from the fiber, that was brilliant scattering?
that what?
Brilliant scattering?
What does that mean? Sorry.
Well, how were you getting the temperature field from the fiber?
Oh, test sensors
Oh,
every 1
what
meter.
was the fiber for?
Transmit laser beam.
Huh?
So the basic idea of this, if I remember correctly, you transmit a laser beam inside the fiber,
Right.
and you get temperature measurement at each sensor along the cable.
Yeah, no,
Yeah.
we had a
You had
talk
it?
on it. It's brilliant scattering
Mhm.
from the thermal variations acting on the photon field, I guess.
Mhm.
Okay.
Okay, guys, thank you so much.
Yeah.